Have you ever wondered why training a neural network feels like trying to solve a Rubik's Cube blindfolded? Why some models fail to converge, or worse, get stuck in a loop of endless mistakes? Well, today we're pulling back the curtain on one of the most fundamental and fascinating concepts in data science: gradient descent. This is your all-access pass to mastering the art and science of neural network optimization. By the end of this video, you'll not only understand how gradient descent works, but also discover techniques to speed up training, tackle overfitting, and navigate the complex loss landscapes that plague so many models. Whether you're a beginner or a seasoned data scientist, this guide is packed with actionable insights that will supercharge your projects. Welcome to the new era of video creation with Jog AI. Simply type your script to get started. Picture this. You're standing in the middle of a giant maze. The walls are towering, the path is foggy, and every turn feels like a gamble. That, my friends, is exactly what it feels like to train a neural network. It's a maze filled with challenges that can stop you in your tracks if you're not prepared. And today, we're going to shine a light on those walls so you can navigate this maze like a pro. Let's start with the big one: complexity of the loss landscape. Imagine this. Every step you take in this maze is based on the slope of the ground beneath your feet. If it's downhill, you know you're moving in the right direction. But what if the ground flattens out, or worse, leads you into a pit? That's exactly what happens with neural networks. Their loss surfaces aren't smooth. They're full of bumps, dips, and flat spots, known as local minima and saddle points. Gradient descent acts like a guide pointing us downhill, but it doesn't guarantee we'll find the lowest point, the global minimum. This means we could end up stuck in one of those pits, unable to climb out. Frustrating, right? But don't worry, I'll show you how to escape those traps later in this video. Now, let's talk about choosing the right learning rate. Imagine you're driving a car down a winding mountain road. If you hit the gas too hard, you'll overshoot the curve and end up in a ditch. If you go too slow, you'll never make it to your destination. Neural networks face the same problem with their learning rate. A learning rate that's too high causes the model to overshoot the minimum, like a car zooming past a sharp turn. Meanwhile, a rate that's too low drags out the training process, wasting time and computational power. Striking the perfect balance here is like finding the sweet spot on a volume knob. Not too loud, not too soft, just right. But how do we find it? Stay tuned, we'll dive into that soon. And then there's overfitting and generalization. Now, think about this like a student cramming for an exam. They memorize every single word from the textbook, but when the questions change slightly, they're lost. Neural networks can behave the same way. They memorize the training data so perfectly that they lose the ability to perform well on new data. This is why techniques like dropout and regularization are critical. They act like forcing the student to study a variety of questions instead of just one type, making the model more robust and adaptable to the real world. All right, now that I've spilled the tea on these challenges, here's a question for you. Which of these have you faced? Maybe you've struggled with finding the right learning rate or felt like your model was trapped in a local minimum. Let me know in the comments. I'd love to hear your battle stories. Now, challenges like these can feel overwhelming. But here's the thing. Gradient descent isn't just another tool in your toolbox. It's the GPS that can guide you through this maze. In the next section, we're diving into how gradient descent simplifies the chaos and brings order to the madness. You don't want to miss this. Now that we've uncovered the challenges, let me introduce you to your new best friend in the world of neural networks: gradient descent. Think of it as your GPS in the maze of training, a methodical guide that ensures you don't just wander aimlessly, but move step by step toward the solution. But what makes gradient descent such a game changer? Let's dive in. Let's start by understanding why we even need gradient descent in the first place. Neural networks operate in high-dimensional spaces, kind of like navigating through a dense jungle, where every tree looks the same. Without a clear path, finding optimal solutions becomes almost impossible, and the terrain, it's rough. Non-convex, lost landscapes with multiple local minima, saddle points, and flat plateaus make this jungle even trickier to traverse. But here's the beauty. Gradient descent isn't afraid of this chaos. It's designed to systematically cut through the noise and lead you toward optimization. So how does it do that? Gradient descent breaks the problem down into bite-sized pieces. Imagine you're lost in the jungle, and every step you take is guided by a compass. This compass points you toward the steepest downhill slope of the loss function, your path to the minimum. But here's the kicker. It doesn't take giant leaps. It moves in small, calculated steps. Why? Because giant leaps could make you miss the optimal path altogether, overshooting your destination. It's this iterative process, step by step, adjustment by adjustment, that makes gradient descent a cornerstone of neural network training. But gradient descent doesn't stop there. It's adaptable. Think of it like a Swiss Army knife for optimization. By tweaking parameters like the learning rate or adding enhancements like momentum, it can navigate even the trickiest landscapes with ease. For example, if the lost surface is as rugged as the Himalayas, momentum helps it build speed in the right direction, pushing through those shallow local minima. And when the road gets bumpy, adaptive techniques like RMSprop or Atom step in, dynamically adjusting the learning rate to maintain a smooth journey. Pretty clever, right? All right. So we've established that gradient descent is your go-to tool for taming the wild jungle of neural network training. But like any tool, its success depends on how well you understand its mechanics. Next, we'll break down the process step by step because when it comes to gradient descent, every detail matters. Let's go. Now that we understand the challenges and how gradient descent can help simplify the process, let's take a closer look at what it actually is. Gradient descent isn't just a fancy term, it's the backbone of training neural networks, ensuring they learn and improve with every iteration. So let's break it down. Training a neural network means optimizing a massive number of parameters. Picture this, you're adjusting thousands, even millions of tiny knobs to find the perfect configuration that minimizes errors. But it's not as easy as it sounds. High-dimensional error landscapes, overfitting, underfitting, and complex lost surfaces can turn this task into an uphill battle. Enter gradient descent, your systematic problem solver. At its core, it's a mathematical optimization technique that iteratively minimizes the loss function, the ultimate measure of how well your model is performing. Here's how it works. At each step, gradient descent calculates the steepest slope, think of it as finding the fastest way downhill, and adjusts the parameters accordingly. It's a methodical, step-by-step approach that ensures your model becomes smarter and more accurate with each iteration. This iterative refinement doesn't just tweak your model's weights, it transforms its ability to perform. Gradient descent reduces errors, enhances accuracy, and streamlines the entire training process. Without it, training neural networks would be like wandering in the dark without a flashlight. By guiding every adjustment, gradient descent ensures your model is always learning, adapting, and improving with every pass through the data. Now that we've introduced gradient descent and how it tackles the challenges of training, it's time to dig into the process itself. How does it start? How does it calculate adjustments? And what makes it such a powerful optimization technique? Let's explore all of that in the next slide. Before we dive into the nitty-gritty of how gradient descent works, let's take a step back and make sure we have the right tools in our mental toolbox. Gradient descent may sound complex, but when you break it down, it's all about understanding three key areas: calculus, linear algebra, and neural networks. Think of these as the building blocks that support everything we're about to learn. First up, calculus. Now, don't let that word scare you. It's not as intimidating as it sounds. At its core, calculus helps us understand how things change, and that's exactly what gradient descent does. We're talking about derivatives, those magical little calculations that tell us the slope of a curve at any given point. When we adjust the weights in a neural network, we're essentially using derivatives to figure out how those adjustments will affect the loss function. It's all about answering one question. Which direction should we move to reduce the error? Next, we have linear algebra. Picture a neural network as a machine that processes data in multiple dimensions. To understand how that machine works, you need to know the language it speaks, and that language is linear algebra. Concepts like vectors, matrices, and matrix multiplication are at the heart of how neural networks process and transform data. Think of it this way. Linear algebra is the GPS that helps data navigate through the layers of the network, making it possible to calculate gradients and optimize the model. Lastly, a basic understanding of neural networks themselves is crucial. This means knowing how layers work, what activation functions do, and the role of forward and backward propagation. If you think of gradient descent as the brain behind training, neural networks are the body. Forward propagation passes the data through the network. Backward propagation calculates the gradients, and gradient descent uses those gradients to fine-tune the weights. Without understanding this flow, gradient descent can feel like solving a puzzle without seeing the full picture. With these foundational concepts in place, you'll be ready to not just understand gradient descent, but truly master it. So now that we're equipped, let's move on to explore the role of loss functions in optimization. They're the compass guiding our every step. All right, now that we've covered the prerequisites, let's talk about the guiding light for gradient descent. Loss functions. Think of a loss function as the GPS signal in our optimization journey. It tells us how far off we are from the right path and points us in the direction we need to go. Without it, gradient descent wouldn't know where to begin or how to improve. Let's break this down step by step. So, what exactly is a loss function? Simply put, it's a mathematical way to measure how well or how poorly a neural network is performing. Imagine you're shooting arrows at a target. The loss function tells you how far off the arrow landed from the bullseye. The further away you are, the higher the loss. The closer you get, the lower the loss. There are different types of loss functions for different tasks. For example, mean squared error, MSE, is perfect for regression tasks, where we're predicting continuous values like stock prices or temperatures. It measures the average squared difference between the predicted and actual values, penalizing larger errors more heavily. Cross-entropy loss is the go-to for classification problems, where the model predicts probabilities for different categories. It evaluates how far off the predicted probability distribution is from the actual labels. Now here's where it gets exciting. Once we calculate the loss, we use it to compute gradients, those magical directions for adjusting the weights. Think of gradients as the steering wheel for our optimization process and the loss function as the map that tells us where to steer. A well-defined loss function not only ensures that gradient descent knows which way to move, but also helps it converge toward a local minimum, and as the model trains, the loss steadily decreases, guiding the network closer to its optimal state. Imagine training a neural network to recognize handwritten digits. If the model predicts a 7 when the input is actually a 9, the loss function immediately flags that as an error and tells gradient descent to adjust the weights accordingly. This cycle repeats with every training example until the network gets it right. And that's the beauty of loss functions. They drive the entire learning process. So now that we understand how loss functions act as the compass for gradient descent, it's time to focus on the next big piece of the puzzle: learning rates. because even with the best map, if you move too fast or too slow, you might never reach your destination. Let's explore how to master learning rates in the next slide. Now that we've seen how loss functions guide gradient descent, let's talk about the speed of the journey, learning rates. Think of the learning rate as the gas pedal in your optimization car. It determines how fast or slow you move toward the solution. But here's the thing, pressing too hard or too lightly can completely derail your progress. Let's dive into why learning rates matter so much. At its core, the learning rate is a hyperparameter that controls the size of the steps gradient descent takes when updating the model's weights. A small learning rate takes baby steps, inching closer to the minimum, while a large learning rate makes big leaps. The goal is to find the perfect balance, just the right step size that moves us closer to the solution without overshooting or wasting time. Let's unpack the consequences of getting this wrong. A small learning rate. Imagine walking through a marathon at a snail's pace. You'll eventually reach the finish line, but it'll take forever. That's what happens when the learning rate is too low. It leads to slow convergence, requiring more iterations to minimize the loss. A large learning rate. On the flip side, imagine sprinting downhill without watching where you're going. You'll overshoot the turn, crash, and lose your way. In the same way, a high learning rate can cause the model to oscillate around the minimum or diverge entirely. Let's unpack the consequences of getting this wrong. A small learning rate. Imagine walking through a marathon at a snail's pace. You'll eventually reach the finish line, but it'll take forever. That's what happens when the learning rate is too low. It leads to slow convergence, requiring more iterations to minimize the loss. A large learning rate. On the flip side, imagine sprinting downhill without watching where you're going. You'll overshoot the turn, crash, and lose your way. In the same way, a high learning rate can cause the model to oscillate around the minimum or diverge entirely. So, how do we find the ideal learning rate? Start with common values like 0.01 or 0.001 and experiment. Use validation sets to monitor how the model performs and tweak the rate as needed. And here's a pro tip. Try learning rate schedules like exponential decay or step decay to dynamically reduce the rate as training progresses. It's like gradually easing off the gas pedal as you approach the finish line. One of the best ways to understand learning rates is by visualizing them. Imagine a graph of the loss function over time. A well-chosen learning rate will show a smooth, steady decline in loss, a clear path to convergence. A poorly chosen one will either flatline or bounce chaotically. These visuals give you instant feedback on whether your learning rate is working. Now that we know how critical learning rates are, let's move on to see how gradient descent actually works in practice. What's the step-by-step process for minimizing errors and improving performance? Let's explore that next. Now we've explored the building blocks, loss functions, learning rates, and adaptive techniques, but how does it all come together? This is where the magic of gradient descent truly unfolds. Let's walk through the step-by-step process of how gradient descent iteratively minimizes errors and fine-tunes your neural network to perfection. Now we've explored the building blocks, loss functions, learning rates, and adaptive techniques, but how does it all come together? This is where the magic of gradient descent truly unfolds. Let's walk through the step-by-step process of how gradient descent iteratively minimizes errors and fine-tunes your neural network to perfection. Everything starts with random initialization. Imagine you're beginning a puzzle. You don't know the final picture yet, so you randomly place pieces on the board. Similarly, the weights of a neural network are initialized randomly. This randomness ensures that the model isn't biased toward any specific direction from the start and can explore diverse features in the data Once the weights are initialized, it's time to calculate the loss. Think of this as grading the network's first attempt at solving the problem. Using a loss function like mean squared error, MSE, or cross entropy, the model quantifies how far off its predictions are from the actual target values. The higher the loss, the worse the prediction. Simple as that. Now comes the heart of the process, computing gradients. Remember the compass analogy? This is the step where gradient descent determines the steepest slope that will take us closer to minimizing the error. Using backpropagation and the chain rule of calculus, it calculates how much each weight contributes to the overall error. This insight is the roadmap for the next step. Finally, we update the weights. Based on the computed gradients and the learning rate, the model adjusts its weights, moving in the opposite direction of the gradient to reduce the loss. It's like taking that step downhill in our optimization maze, closer to the solution with every iteration. And this isn't a one-time process. It's repeated again and again, refining the model's performance over time. What's beautiful about this process is how it brings everything together. Each iteration improves the model incrementally, fine-tuning its parameters until it learns to make accurate predictions. This iterative cycle, calculate loss, compute gradients, update weights, is what transforms a raw neural network into a powerful problem-solving tool. Now that we've laid out the step-by-step process, wouldn't it be amazing to see it in action? Let's bring this concept to life with visualizations that show how gradient descent navigates the loss landscape and converges toward the optimal solution. Let's dive in. All right, we've talked about the theory and the process of gradient descent, but let's be honest. Sometimes words aren't enough. To truly understand how gradient descent works, we need to see it in action. Visualizations can bring this entire process to life, helping us grasp how the algorithm navigates the loss landscape and converges on the optimal solution. Let's break it down. Imagine a 3D map of a mountain range. Each peak and valley represents different configurations of weights in the neural network, and the goal is to find the lowest valley, the global minimum. The loss function surface provides this map, showing how the loss changes with different weight values. It's the foundation for understanding how gradient descent moves. Now picture this, a hiker navigating the mountain range. The size of their steps, whether they tiptoe or take long strides, depends on the learning rate. A small learning rate results in cautious, precise movements, slowly inching toward the minimum. A large learning rate, on the other hand, risks leaping past the target or bouncing chaotically. Visualizing these dynamics helps us see how the learning rate impacts convergence speed and stability. But the most fascinating part is seeing the algorithm adjust weights iteratively. Step by step, it moves downhill, following the gradient, recalculating the loss at each step, and getting closer to the minimum. An animated sequence of this process shows how the path becomes smoother and more focused as the model learns. It's like watching a detective piece together clues, narrowing in on the solution. Finally, let's talk about the convergence path. On a graph, this looks like a trail winding down to the lowest valley. If the learning rate is well tuned, this path is smooth and steady, avoiding overshooting or oscillation. But if things go wrong, such as starting with a poorly chosen point or using an improper learning rate, you'll see erratic or stalled movement. These visualizations provide immediate feedback, helping you refine your training process. So why do these visualizations matter? Because they help us see what's happening under the hood. They reveal whether the learning rate is too high, whether the algorithm is stuck in a local minimum, or whether it's converging as expected. In real-world applications, understanding these dynamics can mean the difference between a model that works and one that fails. Now that we've visualized how gradient descent navigates the loss landscape, let's tackle one of the trickiest parts of training, choosing the right learning rate. How do you find that perfect balance between speed and stability? Let's explore that next. Choosing the right learning rate is like setting the pace for a marathon. It can make or break your training process. Go too fast and you'll burn out, or in this case, overshoot the minimum. Go too slow and you'll never finish the race. The learning rate is one of the most critical hyperparameters in gradient descent, and today we're going to unlock the secrets to finding that perfect balance. So how do you choose the ideal learning rate? Here are a few tried and tested strategies. Start with common values. A good starting point is often 0.1, 0.01, or 0.01. Experimenting with these values can give you a baseline for further fine-tuning. Use learning rate schedulers. Techniques like exponential decay or step decay adjust the learning rate dynamically during training. For example, exponential decay gradually reduces the rate over time, allowing for finer adjustments as the model approaches convergence. Try a learning rate finder. This is a tool that systematically increases the learning rate during an initial phase of training and plots the loss. By observing the loss curve, you can pinpoint the range where the learning rate is most effective. Once you've chosen a learning rate, it's crucial to monitor the training process and adjust if necessary. Here's how: track training progress. Keep an eye on metrics like loss and accuracy. If the loss oscillates wildly or increases, your learning rate might be too high. If progress feels painfully slow, it might be too low. Employ validation techniques. Use cross-validation to evaluate how the learning rate impacts generalization. This ensures your model performs well on unseen data, not just the training set. Think of this like tuning a musical instrument. If the strings are too loose, the sound is off-key, just like a learning rate that's too low. Tighten too much and the strings snap, much like an overly aggressive learning rate. The key is to fine-tune until everything resonates perfectly. Now that we've uncovered the secrets to choosing the right learning rate, let's address another big challenge in gradient descent: local minima. How do we avoid getting stuck in these suboptimal traps and ensure our model finds the best solution? Let's dive in. All right, let's talk about one of the biggest hurdles in neural network training: local minima. Imagine climbing down a mountain to reach the lowest valley, but along the way you get stuck in a shallow dip. You think you've reached the bottom, but in reality, you're far from it. That's exactly what happens when gradient descent gets trapped in a local minimum, and it can significantly impact your model's performance. Local minima are those deceptive dips in the loss landscape where the model seems to converge, but it hasn't reached the optimal solution. They're especially common in complex, high-dimensional loss surfaces, exactly what we deal with in neural networks. The danger here is that the model can't escape these points without additional help, leaving it underperforming on tasks that require global optimization. Thankfully, we have tools and techniques to help gradient descent find its way out. Momentum. Think of it like giving your optimizer a push. By incorporating momentum, gradient descent gains extra speed in the right direction, helping it roll out of shallow dips and avoid getting stuck. Adaptive learning rates. Algorithms like ADAM or RMS-prop adjust the learning rate dynamically. If the optimizer slows down in a local minimum, these methods step in to keep things moving. Random restarts. Another approach is to restart the process from different starting points. This can sometimes help find better paths that lead to the global minimum. For instance, in image recognition tasks, getting stuck in a local minimum might mean your model misses subtle but important patterns, like distinguishing between a cat and a dog in challenging lighting conditions. Avoiding local minima ensures your model learns those fine details and performs with greater accuracy. Now that we've tackled local minima, let's focus on speeding up convergence. Because even with the best path, slow training can waste valuable time and resources. In the next slide, we'll explore techniques to boost convergence without sacrificing performance. All right, let's shift gears and talk about something every data scientist loves: speeding up convergence. We've all been there, waiting hours or even days for a model to train. But what if I told you there are proven techniques to accelerate the process without compromising accuracy? Let's dive into 3 key strategies to improve convergence speed. First, we have learning rate optimization. Remember how the learning rate controls the size of the steps gradient descent takes? Optimizing this can make a huge difference. Here's how: use adaptive learning rates like ADAM or RMSprop. These algorithms adjust the learning rate dynamically based on training progress, ensuring the optimizer moves efficiently through different phases of the loss landscape. Implement learning rate schedules such as exponential decay or step decay. These gradually reduce the learning rate as the model gets closer to the minimum, allowing for finer adjustments and better precision. Next up is batch size selection. Imagine training in bite-sized chunks instead of all at once. That's the idea behind mini-batch gradient descent. It balances speed and stability. Using smaller batches can reduce memory usage and make updates more frequent, which often leads to faster convergence. But be careful, too small of a batch size can introduce noise, while too large of a batch size can slow things down. Experimenting with different batch sizes is key to finding the sweet spot for your specific task. Finally, let's talk about regularization techniques. While they're often used to prevent overfitting, they also play a role in speeding up convergence. Dropout layers force the model to focus on robust patterns, which can streamline the learning process. Weight decay, a form of L2 regularization, penalizes large weights, encouraging simpler, more efficient models that converge faster. For example, in NLP tasks like text classification, combining a well-tuned learning rate schedule with mini-batch training can cut training time in half while still delivering high accuracy. And by adding dropout layers, you can prevent the model from getting bogged down by irrelevant noise in the data. Improving convergence speed is a game changer, but it's not the only challenge we face. Sometimes issues like slow convergence or overshooting can sneak in. How do we address these common problems? Let's explore that next. Even with the best tools and strategies, gradient descent doesn't always behave as planned. It's like trying to assemble IKEA furniture. You've got the instructions, but things still go wrong. In machine learning, 2 of the most common issues are slow convergence and overshooting. These challenges can stall your progress or even derail your training entirely. So let's break them down and see what's really happening under the hood. First, let's talk about slow convergence. Imagine trying to cross a desert while walking at a snail's pace. It's exhausting, and it feels like you'll never reach your destination. That's exactly what happens when the learning rate is too small or the initial weights aren't well chosen. With a small learning rate, gradient descent takes baby steps, inching toward the minimum. While it might get there eventually, it could take an eternity, especially when navigating a complex loss landscape full of hills, valleys, and plateaus. This often results in prolonged training times, which isn't ideal when resources are limited. On the flip side, we have overshooting. Picture this. You're on a ski slope, but instead of carefully steering toward the lodge, you zoom past it and crash into the snowbank. That's overshooting in a nutshell. When the learning rate is too high, gradient descent takes leaps that are too big, often skipping over the minimum entirely. This leads to erratic loss values that bounce around wildly instead of steadily decreasing. The result? Your model doesn't converge, and training becomes a chaotic guessing game. Both slow convergence and overshooting can cost you time and accuracy. Slow convergence eats away at your computational budget, while overshooting can make your model unreliable, as it fails to stabilize and learn effectively. And the kicker? These issues often go unnoticed until you're deep into training. For example, in image classification tasks like recognizing handwritten digits, slow convergence could mean waiting hours for a model to finish training. Overshooting, on the other hand, might result in predictions that jump between classes, like mislabeling a 7 as a 1 because the model hasn't settled into a stable loss. Welcome to the new era of video creation with Jog AI. Simply type your script to get started. Now that we've identified these common pitfalls, let's focus on the solutions. How can we speed up convergence without sacrificing accuracy? And how do we prevent overshooting while still moving efficiently toward the minimum? The next slide has all the answers. Let's take a look. All right. We've talked about the frustrations of slow convergence, those moments when your model feels like it's crawling toward the finish line, but don't worry, slow convergence isn't a dead end. There are proven strategies to speed things up and make your training process far more efficient. Let's dive into the solutions. The first and most impactful fix is adjusting the learning rate. Think of this as setting the perfect pace for a marathon, not too fast, not too slow, but just right. Dynamic learning rates. Techniques like ADAM and RMSprop are your best friends here. These optimizers adapt the learning rate on the fly, increasing it when progress slows and decreasing it when finer adjustments are needed. Learning Rate Finder. Here's a pro tip. Use a learning rate finder at the start of training. It systematically tests various learning rates and helps you pinpoint the optimal range for faster convergence. It's like testing gears on a bike before hitting the road. Next, we have batch normalization. This is like adding shock absorbers to your optimizer. It stabilizes the ride and helps your model move faster. Here's how it works. By normalizing the inputs to each layer, batch normalization reduces internal covariate shift, making gradient descent more efficient. This technique ensures that the gradients flow smoothly, speeding up convergence and improving stability. It's especially powerful in deep networks where convergence can otherwise drag on. Finally, let's talk about early stopping and regularization. With early stopping, you monitor the validation loss and halt training as soon as it starts increasing. This not only saves time, but also prevents overfitting. Regularization techniques like L1 and L2 help by penalizing large weights, encouraging simpler models that are easier to optimize. The result? A faster, more efficient training process that doesn't sacrifice accuracy. Finally, let's talk about early stopping and regularization. With early stopping, you monitor the validation loss and halt training as soon as it starts increasing. This not only saves time, but also prevents overfitting. Regularization techniques like L1 and L2 help by penalizing large weights, encouraging simpler models that are easier to optimize. The result? A faster, more efficient training process that doesn't sacrifice accuracy. Now that we've tackled slow convergence, let's move on to its chaotic cousin, overshooting. How do you rein in gradient descent when it's jumping all over the place? Stick around, because the next slide has the answers. You're driving down a winding mountain road, trying to reach the lodge at the base. But instead of taking careful turns, you're slamming on the gas, overshooting every corner, and careening into the bushes. That's what overshooting looks like in gradient descent. Chaotic, erratic, and completely off course. The good news? With the right strategies, we can turn that wild ride into a smooth journey. Let's explore how. First up, adaptive learning rates. Think of these as cruise control for your optimizer. Algorithms like ADAM, RMSprop, and AdaGrad automatically adjust the learning rate based on how the training is progressing. Here's how they help. If the optimizer detects that it's moving too fast, jumping wildly over the loss landscape, it slows things down, allowing for more precise adjustments. If progress slows to a crawl, it picks up the pace, keeping the training efficient. For example, ADAM combines the best of momentum and adaptive learning, smoothing the path while dynamically adjusting step sizes. It's like having an experienced co-pilot who ensures you're always on the right track. Next, we have learning rate schedulers. Imagine starting a long-distance run at a sprint. You're bound to burn out, but if you pace yourself and gradually slow down, you'll reach the finish line with energy to spare. That's the idea behind learning rate schedulers. Here are some popular techniques. Exponential decay. This reduces the learning rate by a small percentage after every epoch, ensuring finer adjustments as the model nears the minimum. Step decay. At predefined intervals, the learning rate drops significantly, allowing for a controlled and stable descent. Cosine. Annealing. This technique gradually decreases the learning rate following a cosine curve, bringing it close to zero as training completes. Using schedulers, you can prevent overshooting while still exploring the loss landscape efficiently, especially during the early stages of training. Now, here's where things get exciting. You don't have to choose just one of these solutions. In fact, combining adaptive learning rates with a scheduler can give you the best of both worlds. Imagine using Atom for its dynamic adjustments while layering in exponential decay to refine the learning rate over time. It's a 1-2 punch that keeps training fast and precise. Let's bring this to life with an example. Say you're training a model to classify images of handwritten digits, a task where accuracy is everything. Without these solutions, overshooting might cause your model to misclassify a 9 as a 4 or bounce back and forth between predictions. But by using a scheduler to reduce the learning rate and an optimizer like RMSprop to control the step sizes, you can smooth the training process and achieve stable, reliable results. Now, imagine a graph of the loss function over time. With no adjustments, the loss bounces around unpredictably, a chaotic zigzag with no clear pattern. But introduce adaptive learning rates and a scheduler, and the graph transforms into a smooth, steady curve, converging gracefully to the minimum. That's the power of these techniques in action. With overshooting under control, you've unlocked a critical piece of the gradient descent puzzle. So far, we've tackled slow convergence, local minima, and erratic behavior. Now it's time to take a step back and recap why mastering gradient descent is so essential for neural network training. Let's wrap it up in the next slide. All right, we've taken quite the journey together, from understanding the challenges of neural network training to mastering the nuances of gradient descent. Let's take a step back and connect the dots. Why is mastering gradient descent so crucial for machine learning? Spoiler alert, it's the secret sauce that powers nearly every neural network success story. Here's why. First, let's remember how gradient descent simplifies training. Imagine you're trying to find the shortest path through a dense forest. Without gradient descent, you're wandering aimlessly, hoping to stumble across the exit. But with gradient descent, it's like having a guide who knows the way, adjusting weights iteratively to minimize errors and leading you straight to the solution. It's this systematic approach that makes training manageable, no matter how complex the model or dataset. Gradient descent isn't just a tool. It's the backbone of machine learning optimization. Think about this. Whether you're training a deep neural network for image recognition or a simple logistic regression for binary classification, gradient descent is doing the heavy lifting. By iteratively updating model parameters, it ensures your network learns from data, refines its predictions, and becomes more accurate with every step. Without gradient descent, the concept of optimization would fall apart, leaving us with models that don't improve. And here's the best part. It's not just about finding a solution, but about finding it efficiently. Gradient descent, combined with techniques like learning rate optimization and regularization, allows you to train models faster and smarter. Think of it like this. Instead of stumbling your way to the finish line, you're sprinting there with precision and control. It avoids pitfalls like local minima, handles complex loss landscapes, and ensures your model reaches peak performance without wasting time or computational resources. Let's ground this in reality. Whether it's building a chatbot to improve customer service, detecting fraud in financial transactions, or diagnosing diseases with medical imaging, gradient descent is the invisible force driving these breakthroughs. By mastering its principles, you're unlocking the ability to train models that aren't just accurate, but also efficient and scalable. So what's the takeaway here? Gradient descent isn't just a mathematical algorithm, it's the cornerstone of machine learning. It transforms the daunting process of training into a systematic journey, guiding your model from randomness to precision and from guesswork to intelligence. Now that we've revisited why gradient descent is so essential, let's summarize the key lessons we've covered in this journey. What have we learned, and how can you take these insights forward? Let's recap everything in the next slide. We've covered a lot of ground, haven't we? From the initial challenges of training neural networks to the fine-tuned solutions for speeding up convergence and avoiding pitfalls, we've explored the entire landscape of gradient descent. Now, let's bring it all together and highlight the key takeaways you can carry forward. First, we started by addressing the challenges. Training neural networks isn't easy. It's like navigating a maze of high-dimensional data with non-convex loss landscapes that make optimization tricky. This understanding set the stage for everything else we explored. Knowing the problem is half the battle, right? Then, we uncovered the hero of our story, gradient descent. It's not just an algorithm. It's the backbone of optimization, iteratively adjusting weights to minimize the loss function. Without it, training neural networks would be like trying to hit a moving target in the dark, impossible. We also talked about the essential skills you need to master gradient descent. Calculus to understand derivatives and gradients. Linear algebra to work with matrices and vectors in multi-dimensional spaces, and a foundational knowledge of neural networks to see how gradient descent fits into the bigger picture. These tools are the keys to unlocking the full potential of optimization. Next, we walked through the step-by-step process of gradient descent, initializing weights, calculating the loss, computing gradients, updating weights. This cycle is the engine that drives learning, turning data into insights and predictions. Understanding this process helps you visualize what's happening behind the scenes. We also tackled some common roadblocks like slow convergence, that frustrating crawl toward the minimum, which we solved with techniques like learning rate optimization and batch normalization, overshooting, the chaotic jumping that we fixed with adaptive learning rates and schedulers, and let's not forget avoiding local minima, those deceptive traps that can derail your model entirely. So why does all of this matter? Because understanding and mastering gradient descent equips you to train better models faster. It's the foundation for building intelligent systems, whether you're working on NLP, computer vision, or predictive analytics. The skills you've gained here are directly applicable to solving real-world problems and driving innovation. Now that we've summarized the key points, it's time to think about applying them. How do you take everything you've learned and put it into practice in your own projects? The next slide will guide you through the practical steps to start implementing gradient descent like a pro. We've explored the theory, strategies, and solutions for gradient descent, but now comes the exciting part, putting it all into action. How do you apply what you've learned to train real-world neural networks, whether you're working on a personal project or a large-scale enterprise system? These practical steps will set you up for success. Before diving in, let's revisit the foundation. What is gradient descent? It's a mathematical optimization technique used to minimize the loss function by iteratively adjusting model weights. Why is it important? Because it's the core of training neural networks, helping them learn from data, reduce errors, and improve performance. By understanding these basics, you're already ahead of the curve and prepared to take on the challenges of real-world implementation. Now let's talk tools. For implementing gradient descent, you'll need a few key components. Frameworks like TensorFlow or PyTorch. These libraries handle the heavy lifting, from automatic differentiation to efficient matrix operations. A dataset that fits your use case, Whether it's image classification, text processing, or regression, the quality of your data is just as important as the algorithm itself. Pro tip: start with a simple data set like MNIST or IRIS to build confidence before scaling up to more complex tasks. Next, it's time to configure the hyperparameters. Remember, these are the dials you can tweak to control how gradient descent operates. Learning rate. Choose an initial value. Common options are 0.1, 0.01, or 0.001, and adjust as needed using schedulers or dynamic optimizers like atom.batch size. Experiment with different batch sizes to balance speed and stability. Mini batches often work well for most applications. Think of this step like fine-tuning a car engine. You're optimizing for both speed and efficiency. Now that your model is training, it's time to keep an eye on its performance. Use metrics like loss and accuracy to evaluate progress. A steadily decreasing loss is a good sign you're on the right track. Watch for signs of trouble. If the loss plateaus, slows down, or oscillates, revisit your hyperparameters or optimize a choice. Here's a tip. Visualizing the loss curve can provide instant feedback on how well gradient descent is performing. If the curve is smooth and declining, you're in great shape. If it's jagged or flat, it's time to troubleshoot. Let's say you're building a model to predict housing prices. You set up your environment with TensorFlow, load a dataset with features like square footage and location, and configure gradient descent to minimize the mean squared error loss. By tweaking the learning rate and batch size, you achieve convergence in half the time it would have taken with default settings. Monitoring the loss curve ensures you stay on track, delivering a model that's both accurate and efficient. With gradient descent implemented successfully, you're now ready to share your experiences and insights. How did your model perform? What challenges did you face? And how did you overcome them? The next slide is all about reflecting on the journey and showcasing how gradient descent has empowered your work. Let's take a moment to reflect on your journey with gradient descent. Whether it's been smooth sailing or a roller coaster ride, there's always something to learn and share. Sharing your experiences isn't just about showcasing your successes. It's about learning from challenges and helping others navigate their own paths. So, what does a real-world gradient descent journey look like? Training a neural network often feels like exploring uncharted territory. The error landscape is complex, filled with local minima and saddle points that can easily trap an optimizer. Maybe you've encountered a model that got stuck, leaving you scratching your head. But here's the thing. Overcoming those challenges is what makes your journey valuable. It's the struggle that sharpens your skills. In every project, gradient descent plays the role of the navigator. By iteratively adjusting weights, it takes you closer to the global minimum, even if the path is full of twists and turns. Think back to a moment when you tweaked the learning rate, added regularization, or adjusted the batch size, and suddenly the loss started dropping. That aha moment is the magic of gradient descent in action. Of course, the best part of the journey is reaching the destination, a model that performs well, whether it's classifying images, predicting stock prices, or generating text. Sharing how you got there, what worked, what didn't, and the insights you gained along the way can inspire others to refine their own approaches. Here's an example. Imagine a healthcare project where gradient descent was used to train a model for detecting early signs of disease. By fine-tuning the learning rate and using adaptive optimizers, the team achieved rapid convergence and built a system that saves lives. Or take an NLP project where dropout and regularization helped prevent overfitting, resulting in a chatbot that delivers precise, human-like responses. Sharing your experiences isn't just about showcasing what you've learned. It's about contributing to the broader community. Post your findings on platforms like LinkedIn, write blog articles, or engage in discussions on GitHub or Kaggle. The insights you share could be the breakthrough someone else needs. Now that we've reflected on the journey and shared our stories, let's focus on how we can continue learning. The field of neural network optimization is vast, and there's always more to explore. In the next slide, we'll look at resources and strategies for deepening your expertise and taking your skills to the next level. Here's the thing about machine learning. There's always more to learn, explore, and experiment with. Gradient descent is just one piece of the puzzle. If you want to take your skills to the next level, it's time to dive deeper into the world of neural network optimization. So, where do you go from here? Let me guide you. First, revisit the challenges we've discussed. Overfitting, where your model performs too well on training data but struggles with new data. Underfitting, when your model doesn't learn enough to make accurate predictions. And slow convergence, which tests your patience and resources. Understanding these challenges deeply will help you identify and solve them faster in your projects. Next, explore the various types of gradient descent. Batch gradient descent, great for stability, but computationally heavy. Stochastic gradient descent, SGD, faster updates but noisier progress. Mini-batch gradient descent, the perfect middle ground for most tasks. Each method has its strengths and trade-offs, so dive deeper to understand which works best for your specific use cases. Once you've mastered the basics, step into advanced optimization algorithms like ADAM, a fan favorite for its adaptive learning rates, RMS-prop, ideal for non-stationary loss landscapes. AdaGrad, perfect for sparse data. These algorithms build on gradient descent, adapting to the challenges of modern neural networks and making training faster and more reliable. The best way to learn? Apply what you know. Work on datasets like MNIST, CIFAR-10, or even custom datasets tailored to your projects. Experiment with different learning rates, batch sizes, and regularization techniques. The more you practice, the better you'll understand how these tools interact in real-world scenarios. Finally, keep learning with these resources. Books. Deep Learning by Ian Goodfellow is a must-read, as is Michael Nielsen's Neural Networks and Deep Learning online courses. Platforms like Coursera and Udemy offer hands-on tutorials for gradient descent and optimization techniques. Communities. Engage with fellow learners and practitioners on Kaggle, GitHub, or LinkedIn. Share your insights and learn from others. It's a two-way street. The beauty of machine learning is that it's an endless frontier. There's always a new algorithm, a new dataset, or a new problem waiting to be solved. By mastering gradient descent and continuously expanding your knowledge, you're not just building better models, you're building a stronger foundation for innovation. Before we wrap up, I want to hear from you. What's the next step in your learning journey? Drop your goals in the comments below. And if you found this video helpful, don't forget to like, share, and subscribe to stay updated on more content like this. Let's keep learning and growing together.